Good afternoon. Now I think only one topic is remaining to complete this. The topic is inverter techniques, correct? Inverters, how to understand is the concept. After that, we'll take a small break again, and after that, we'll complete the two problems. So today, a small announcement for you. For tomorrow class, due to this offline classes has been started in Hyderabad. Okay, due to that, there is some timing problem tomorrow. So tomorrow, I'm thinking that I have to complete earlier tomorrow at 4 o'clock. They have given time for me. That's why I'm expecting tomorrow. We'll take class for tomorrow. Please note on this timing. 8 I'll start tomorrow. 1 hour early will start, and we are going to close the matter tomorrow by 4 p.m. Because after 4 p.m., some other faculty has to take the class here. That's why 4 p.m. they said, that's why I shifted 1 hour before tomorrow. Only for tomorrow. Day after tomorrow we'll see according to the timing. For tomorrow the class timing is slightly different. Morning 8 o'clock, evening 4 o'clock sharply I have to stop the class. Because after 4 some other teacher will take class in the sport. So I think tomorrow by 4 o'clock we'll be free. Is it okay for you? Morning 8 will start. Daily we are starting at 9. Please tomorrow we'll start at 8. You know 8 o'clock means 8 to 9:30. I'll try to take one class and I'll use small break for you. Half an hour break for breakfast. So no worries. So very good afternoon to all of you. I hope you understood the timing. So it is morning 8 to 4 o'clock. Tomorrow timing. Just send one message also. Tomorrow timing. Tomorrow timing is 8 to 4 p.m. Only for tomorrow. Okay? Morning 8 o'clock, evening 4 o'clock. I'll end up the class tomorrow. So let us start our concept now. Let us start our concept. So keep the heading topic number 3 we are entering. That is called MOSFET. MOSFET inverter design. MOSFET inverter design. This is the last topic of my MOSFET class. Thank you very much for understanding the timing. Okay, so no problem. Tomorrow timing is good. By 4 o'clock we can be free tomorrow. At least we are not getting any holidays. Maybe these are the chances you can take, having some free time to practice your concepts. Okay, 4 o'clock means you have a good time to practice after that. Okay, so then this one topic if I can cover today, we can close the matter of this. MOSFET class will be completed. So keep the heading right on. MOSFET inverter design, which is a completely purely digital design concept. Okay, digital concept it is. Try to see how we try to design it with analog basics. MOSFET inverter design. So first of all, if anybody asks you, can you explain any ideal inverter, how it should be for a transistor? It may be BJT or MOSFET, any transistor you take, how to draw an ideal inverter first. From that we'll try to design practical inverters. So keep the heading, ideal inverter, subheading you can keep. Ideal inverter. So I'm expecting from your MOSFET, this type of inverter design. If you have a MOSFET like this is your MOSFET, this is drain, this is gate, this is source. If I give some input to the gate, if I take some output to the drain, which is working like a switch, you're giving some input here, you're changing the input, you're getting the output. If it want to be an ideal switch, suppose assume that your MOSFET is an ideal switch, suppose we assumed it. Just assume that your switch is ideal. If you are assuming that your MOSFET is behaving like an ideal switch, how the graph we are expecting the class. Okay? So let us see how the graph we can expect. This is your input PIN, this is your output. So this is called as a transverse steady graph for your MOSFET. Input x-axis we are taking, output y-axis. We are changing the input of the switch and what the output response we try to verify today. That's called inverter switching technique. So let us see, first what he's asking is, whenever you are at 0, my input is at 0, when the switch is at 0, the person is saying that the output should be the highest one. Highest in circuit design says VDD. So how much VDD you are going to give, supply to the MOSFET, that much highest value has to come there. So whenever you are at low, the output should be high. That is required for an inverter switch. A common emitter will work like this naturally. Low input, high output will come for common emitter systems. A common source also will give the same impact. But this switching off condition, this switch is off here, that means your MOSFET is in off. The MOSFET should be off. Up to how much time you are expecting? This MOSFET should be off, I know that, but how much time ideal switch requires means when the journey starts 0 to up to VDD by 2. How much supply you are giving? Suppose VDD is given as 5 volts, up to 2.5 volts, 0 to 2.5 volts of my input, it should become off condition. It should become off. Then if you cross VDD by 2 your input, then it's telling that the output has to immediately switch on to on condition. That is, output has to come to low. It has to come to low. So whenever it is coming to low, your MOSFET here will be on. So one is off, one is on. This is the way how the switching characteristic are seen. That means the person is asking 0 to VDD by 2, the switch should be off. Okay? Okay, Samresh. Amplifiers, you don't want me to start today? No problem. Just tell you the topic names at least today and I'll stop the class. Okay? Just the topic names, what topics we have to learn. Just tell you the basic idea so that it will not waste our time for tomorrow class. I think otherwise tomorrow video only separately we can start the topics. But you come 5 minutes before so that you can write all the topic names, all these things. Okay? Don't get worried about amplifiers. Complete this module today. So 0 to VDD, the MOSFET should be off. When your input is coming greater than VDD by 2, the MOSFET should be on. So why you are asking half of the time period off, half of the time period on means the transition between on to off to on should be same. That's called ideal switching. But in between, what you want? In between, how the graph you are expecting means when you are making switch off to on, this boundary, whatever you are seeing, you have to switch off to on, like vertically you have to switch on to off to on. That means in this region, we should not take much time. The transition should be very speed, on to off and off to on. That means the slope of this line should be infinite is required. Okay, that region we call it as your M is in active. So that means you should not give much time in switching electronics. You should not give much time for the transistor to spend the time in active region. That's why vertically you have to move from top to bottom. This is the ideal switching characteristics in digital designs. This is the ideal switching characteristics. So I think my MOSFET is not an ideal MOSFET. It's a practical one. Maybe this type of graph may not come, but to get the type of graph, what to do is analysis. How to modify the circuits and how to apply the ideas such that finally this graph has to come. Okay? If you get this type of graph, you can stop the analysis. You got a good inverter, we can say. Until unless this type of graph is not coming, that will not work as a good inverter. Okay? So that means you're asking here, whatever the gain you are getting here, that gain, voltage gain should be infinite. Infinite gain if you go, this will give a vertical slope there. Okay? This slope is nothing but change in the output by change in the input. This is the slope. So if the gain becomes infinite, automatically that line will become vertical, so that you will get the without any time disturbance, you go on to off to on, we can move directly. So this is called ideal characteristics of inverters. So Divya, that's nothing I have explained. If you have a switch with you, when your input is low, you are applying, the output should come as high. That is called inverter. Low input, high output has to come. When you are reaching to the high input, VDD by 2 after that, the switch comes into on condition, which will work like a short circuit, so output will become 0. This is our switching characteristics. And the point is, this is a vertical line we want. If you don't have vertical line, you are spending some time in active region. Because in switching, on to off to on, we have to move in such a manner, you should not take the time for active region. That's why the slope of the line should be infinite is required. So that means dV naught by dVi, otherwise del V naught by del Vi should be infinite. So V naught by Vi, change is called gain. The gain should be infinite, I'm telling you. Gain is nothing but slope of that line. Should be infinite. Okay? Simply thus, gain is nothing but change in the output by change in the input. That should be infinite. That is nothing but the slope of the line. This is called slope of the line is gain. Slope of that line is infinite is required. Because it's a vertical line. So if we can understand this simple theory, we can start step by step and we'll improve the concept one by one. There are 3 designs now I'm going to teach. The first design is a normal inverter, we can say, with a passive load technique called as resistors. If I take a resistor as a load, then how it will behave, whether it will give the ideal characteristics or not, is the first idea we are going to develop it. They are very easy, okay, don't feel tough, very easy and very comfortable to understand. So slowly you have to understand step by step, there's a new concept. That's why take down clearly the concept. Let us start with my first design calculations. So let us start with the first calculation, okay? So let us start the first one today. Concept number 1. Keep the heading, first topic. NMOS inverter. NMOS inverter with passive load. Passive load. Which is passive load is nothing but RT resistance. So I'm taking just a resistor as a load. What happens? Whether it will behave as a good inverter or not. Just I'll verify it. You can see that this is your MOSFET amplifier. NMOS amplifier I'm taking. This is your load. Resistor load I'm taking. This is RT. This is VDD. This is your input. And this is your output. This is called NMOS inverter. Yes, I have taken a NMOS inverter in the class. Okay? And please remember, the input what I am applying is not AC, it's a DC. It's a DC inverters, not the AC inverters. So these are all concerned to DC inverters we call. We're not doing AC inverters here, this is DC inverters. So the input is also DC, output is also coming as DC. That point don't forget. Okay? Input is a DC I'm changing, output how it will change is our class today. Step by step, try to see the concept clearly. We'll do in 3 steps now. What is the first step? You can see. You take this as VGS, get to source voltage from here to here. And you take this as VDS from this point to this point. This is VDS. Only within 3 steps we'll understand the concept now. Okay, step 1. Step 1 procedure. What is my first condition is 0 less than VIN less than your threshold voltage I have given for this MOSFET. And remember that whatever the inverters you are preparing, we are not taking depletion mode, we have to take enhancement mode. Because enhancement mode are the good switching devices compared to a depletion mode. So in default, these are all enhancement mode MOSFETs. They're all enhancement MOSFETs. This is called enhancement, not the depletion. These are called enhancement MOSFETs. Okay, you can see the first step. What I am doing is my input voltage, whatever the DC I am applying less than the threshold voltage. You know that already in switching, testing, we have done all these things. So I take it as a normal thing. We will apply 0 to VT in between my input. Automatically, the MOSFET cannot get the channel inside because in enhancement MOSFET we don't have any channel. We have to create the channel inside. If you want to create the inversion layer, your input should be greater than threshold voltage you have to do. But initially, 0 to threshold I am analyzing the class. So 0 to threshold, what you can write? 0 to threshold. Your MOSFET M is in cutoff. Your MOSFET M is in cutoff position. If M is in cutoff, can I say that your ID current will become 0 then? That's a very common sense point. Your MOSFET will become cut off between 0 to Vi and between VT, it will be cut off so that no current will flow because it is working as an open switch. When the ID current becomes 0, this is your ID. This is your ID. If ID becomes 0, can I write what is the output here? V out. V out is VDD minus ID into RD. This is your V out. Okay? Here we said that ID is 0 here. It is VDD minus 0 will come. So V out will become VDD. The first point I am successful. When the input is at 0 position, the output we are getting maximum. So I can say it is working as an inverter. It is inverter, I know that, but it should be a good inverter. Ideally, how I have been represented my response. If you get the same response, we say good inverter. It's behaving like inverter. BJT also works like inverter, but we want a good inverter. So how a good inverter will come, we'll see. So 0 to VT, your output will be equal to VDD. First point is very clear. What about the step 2 analysis? If I start thinking about step 2 now. Step 2. So complete up to here. Step 1 is completed. Note on paralleling. Step 1 is cutoff position I understood. 0 to VT, what happens? Manja, how can you answer the question like that here? M is off means cut off or on you are asking. Off means what? We have to say cut off is off. Okay, on means what? It will be going in ohmic region or triode region. We call it as on. Okay, When you are in active region, we call it as current saturation. We are just replica points we are trying to understand. So off means cut off, my friend. Okay, off means cut off. And Shavani Das is asking 0 to VT, how it is cut off. Don't bring me back to the subject here. I'll class morning to evening. I have spent a lot of time for you. And in the recording video, you can see 4 modules I created. Part 1, Part 2, Part 3, Part 4. I have been explained beautifully that an enhancement MOSFET, whenever you are not giving any voltage, there will be no channel is created such that the current will be 0. Basics I have been explained. Again, you are going back and asking me, sir, 0 to VT, how MOSFET is off? That is not good. Okay, if you are confused with that, go back and see the video again and again and understand the point. Okay, yesterday smoothly I covered each and everything. So try to understand in a beautiful manner the content. So 0 to VT, M will be in cutoff. MOSFET cannot be on because channel is not there created. Channel will create only when the input is greater than VT. So the next point here is, suppose if you apply your input, your input VIN is slightly greater than VT. This is the condition I kept. Your input is slightly greater than the threshold voltage. What will happen is MOSFET will create the inversion layer. Okay, MOSFET will have inversion layer will be created. Okay. Jahnavi, enhancement MOSFET is having high switching capacity ODA. Enhancement MOSFETs are good switches compared to the depletion MOSFETs because the diode is an enhancement switch, not the depletion switch. Okay, diode is a good switch. MOSFET is also behaving in enhancement mode like a diode behavior. That's why it is called enhancement is a good idea compared to depletion. So VN is slightly greater than VT. What happens? Whenever the input is slightly greater than VT, what will happen is your output will be slightly less than VDD will come. Your input is increasing, the output is slightly decreasing. From highest to lowest it is decreasing. So then V out slightly decreases from VDD. So this is the story. When your input is increasing greater than the threshold voltage, your MOSFET will come into on. At that time, your output slightly decreases from VDD. Because VDD is the highest, you're decreasing because cutoff condition is over. Now some current is passing here, therefore VDD will be slightly decreasing. Because V out is equal to VDD minus ID into RD. So VN is slightly greater than VD. What happens? Your MOSFET M is on. You can write here, your M is MOSFET, now onwards. Your M is getting on. When M is on, your ID is existing in the class. If your ID is existing, can I say that this value will slightly decrease from VDD value? VDD minus ID RD is V out. So V out is slightly decreasing in the class. So previously V out is VDD we said because ID is 0. Now as the MOSFET came into on, your VDD, your V out value is slightly decreasing from VDD. That's a simple point. Okay. So V out is decreasing. V out is decreasing because your ID is increasing in the class. When the switch gets on, ID current will increase. If ID current increases, your output value will decrease. What I understood is now, this value V out is slightly decreased from VDD, is said, and input value is slightly less than VD. Now you can see that output value is very high value, input value is very less value. With this concept, we can say that your output is coming greater than your input. When the output is having high value, input is low value because it's an inverter. When the input is low, output is already high. So slowly we are increasing the input. At that time, output is a high position. So whenever the output comes greater than the input, you can say that your M is in current saturation. M is in current saturation. That means it is satisfying the condition VD is greater than or equal to VGS minus VT. This condition it is satisfying because V out and VDS both are same. According to the board, V out VDS are same. VIN VGS is same. If you just compare that VDS is greater than VGS, that is enough actually. Minus VT to origin. If it is greater, you're on. And in which region I identified is you're under current saturation. So I understood that immediately when the switch is off first initially, when the input is slightly greater than threshold, you're not going to triode region, you're going to current saturation. That is important. That means the switch is off first. Next it is not going to triode because triode is on condition for us. In between there is a current saturation. So you touch current saturation first. That is the story going on in the concept. Now what is ID relation? We can write for this is. It is Kn into VGS minus VT whole square is a current relation. Now the current is flowing in this manner. Therefore, you can write the V out relation as, your output voltage, you can write it as relation VDD minus ID is Kn into VGS minus VT whole square into RT. Here VGS is nothing but your input voltage. So V out, you can write as VDD minus Kn into VIN minus VT whole square into RT. Now you can see how the behavior of your output with respect to input, I create a relation for it. Satyam and one more person, Shabri Das, थोड़ा common sense use करो. I said that VAN is slightly greater than VT. Common sense here. VT is suppose 0.5. Okay, my input is slightly greater. Means suppose 1 volt you can take. 1 volt input. इधर क्या बोल रहा हूँ? V out is slightly decreasing from VDD. Slightly I said I'm not saying that it decreasing to 0. Then if it is suppose 10 volts VDD, I said slightly decreasing means suppose 9 volts. ये 9 volts है, ये 1 volt. Then how can you say that input is greater than output? Output will be greater than input initial. Because output is at highest, input is started now, lowest to highest you are moving. Okay, Satyam, correct karo concept. Satyam Satya Prakash. Input is not greater than output. Output is greater than input in the first case because slightly you are greater than that. I'm not increasing very high value. Slightly I'm increasing. So that is the story I said. With that, this is a current saturation equation I've written. You can see now your input is increasing here. Your input is increasing. Your output is decreasing. This is the way how your output behavior with respect to input. Your output behavior is like this. This behavior, can I say that it is a non-linear or a linear? Means that this behavior is a non-linear falling. It is like a non-linear. The graph is falling from output to input because parabola is not a linear. It's a non-linear. These all things we'll try to see in the graph afterwards. First, mathematics understand. Initially, it is at highest. After getting into current saturation, the output voltage is falling like a parabola. First point. The output is falling like a parabola. So this is called step 2 analysis. What is step 3? Step 3. What do you mean by step 3 here is there will be some boundary called EYS. EYS means edge of saturation. So you are traveling in current saturation. After that, compulsory you have to come to triode. So at what position you will get into the triode? For that, EYS condition will try to develop. What is EYS condition is your VDS will become VGS minus VD. This is called EYS. Edge of saturation value is boundary limit. Okay, edge of saturation value. So it is just looking like one separate straight line. It is V0 is equal to VIN minus VD. So we are getting one separate line in the graph. This is called a boundary line. So that the current saturation to triode you are moving with the boundary line. So we take it as EYS condition. Now the final point in the class is the final point here. What is that? Last step. Step number 4. What he's telling is if you want to come to triode now, if you want to come to triode, suppose you are interested to come to triode region. If you want to come to triode, what you have to do is your output, whatever you have, should be less than VN minus VD you have to apply. That means you have to apply more and more input voltage such that the output will decrease, your input will increase. So in this case, your output should be less than VIN minus VD. Your range should come like this. Apply the input voltage in such a manner, it should dominate your output voltage. Because you are applying 0 to VDD the input, somewhere it will come this condition. This is boundary condition, this is less than its triode condition. So whenever you reach to this point, when your output is less than input minus VD, you can confirm that your MOSFET is in triode region. So your M is in triode, it will come. Your M is in triode. If the M comes to triode effect, your M, if your M is coming to triode effect, then I think your ID relation, I think I need some gap to move this side. I'm expecting this points you have written, so slightly I'll move it. So you can write here, triode equation is ID is equal to nu n Cox W by L into VGS minus VD into VDS minus half into VDS square. This is your triode equation in the class. This is your triode region equation. This is your triode region. For simplicity, we can write this equation as ID is equal to K and dash, you can write W by L into VGS को हम लिख सकते VIN minus VD into VDS we can write as V0 minus half into V0 square. So nu n Cox I have written as K and dash, which is called MOSFET process transconductance parameter. This total letter from here to here we can write as K and dash, which I defined in yesterday theory classes. K and dash. Okay. So I think VGS place we have written input, VDS place we have written output. So how the relation you can write is your output is equal to VDD minus ID into RD. So this is your output equation. So output is equal to VDD minus K and dash W by L VIN minus VD into V0 minus half into V0 square into RD. So this is the way how you are getting the again output relation with respect to input. In triode region, I think this is the way how the current is, how the voltage is falling down again. Your input is increasing here, your output is falling here. So slightly the output follows in triode effect. And this effect is also looking as non-linear again. So you are getting non-linearity not only in current saturation, in triode also we are getting non-linearity. This is a complete mathematics to understand the concept. So if you complete this, I'll show you the graph, what we have been understood till now. Mathematics, I'll show you like a graph. This is a complete equation sequence. The total board is covered with a complete approach. Only 4 steps I explained. First step is cutoff. Second step is current saturation. Step number 3 is EYS. Step number 4 is triode. Total 4 cases will come. So they're very easy to understand. They're not very tough to do these problems. Try to understand the principle. Definitely you'll do these questions well. The principle is good. The board is clear for you, or shall I magnify it? This part if you want, I'll magnify it. Step 2 onwards, I'll magnify it otherwise. Step 2 onwards you can see. I'm expecting up to step 1 you have been written. Iron drawing. Why this switch? Why we are not calling this a switch? Why we call it as inverter means common sense here. Board take up feeling ajana. When the input is low, we apply it. The output came as high. What is the meaning of inverter? At your home also, if the power supply is off, suppose your current is failure. Also you are getting on all the switches. What is the reason? We kept the inverters or not at home. That means when your load becomes low, it will become, when the input becomes low, output will become high. That is called inverter techniques. So it is a switch also, it's an inverter also. Okay, inverter is a word comes. Inverter is nothing but when input is low, output is high. When input is high, output will be low. That concept we call it as inverter switching. It's a switch only here, okay? But it's an inverter switch. If not one switch, if I give input low, output is also low. If I give input high, output will be high. But this switch's specialty is they work like an inverter switch. Low to high to low, they work. Yeah, visual, I have been magnified it. I think more than this I cannot magnify it. Let's see. can see, otherwise this much I can magnify for you. Some are seeing in mobile, okay? So you can see this. So please complete up, okay? If you are completed, please tell me. I'll proceed for the graph for this. Inverted graph will write. And we'll see what is the trouble in this graph. We'll rectify that concept. Only 3 steps I said here, nothing more than that. Initially, it is in cutoff. After when you cross the threshold voltage, you are going to current saturation. After that, there is some boundary, EYS. When you cross that boundary, you will go to the triode region. Okay? In all the cases, the output is decreasing when the switch came into on condition. Very easy topic it is, nothing to get tension on this area. This is the backbone concept of digital designs. So let us see the graph. You can see the graph on there. This is the characteristic graph called transfer characteristics. This is your input. Your output is here. You take this as 0 and the maximum boundary of my input is VDD. I want to change from 0 to VDD as my input. Okay? I treat it as VDD as high, 0 as my low. But what is happening in practical MOSFETs is up to threshold only this MOSFETs are telling will be off. So up to threshold voltage the MOSFET is telling I'll be off. So this answer will come as highest value from 0 to threshold voltage we are getting. But how you have been given me ideal theory is it has to switch off from 0 to VDD by 2 you said. That means it has to switch off from here to center of the value VDD by 2. But in normal switches like MOSFETs, they cannot do that work because they'll get just on when you cross the threshold voltage. That is the problem we are getting in the concept. 0 to VDD only they are getting off. We are getting transistors open circuit, so we are getting the highest voltage VDD. Up to here we are getting VDD. So your MOSFET M is in cutoff here. MOSFET is in cutoff. If your MOSFET is in cutoff, your output here is coming as VDD. Highest value we are getting from 0 to VDD. So after that, we have one more line, we got boundary line we can say. Some line we got like this. This boundary line is V0 is equal to VIN minus VT. This boundary line we call it as EYS line. Edge of saturation line in step 3 we have created. This boundary line what it will tell is above this current saturation, below this a triode. So how the voltage is falling here is non-linearly falling like a parabola he said. So because it's a parabola equation, so this is called current saturation behavior at output. Your output is just falling like a parabola. Because our equation is Kn into Vi minus Vt whole square. So it will fall like this output. But when it touches this line up to this point, your current saturation is over. Here the current saturation is over. So here M will be in current saturation in this region. Your M is in current saturation. Your M is in current saturation. Where your output is decreasing with respect to your input is increasing. Your output decreases as the input increases in this concept, like a non-linear behavior. When it touches this point, again, it will go to triode effect. Triode also is a non-linearity where it is falling like this. Non-linearity is also in the similar manner, it's falling towards the 0. So here M will be in triode. Triode is nothing but on switch. Triode means on switch. Your output is again falling with respect to input is increasing. So this is the way how we got NMOS inverters with passive load techniques. So whatever you studied mathematically, you can see each step in the board. This is called step 1, this is called step 2, this is called step 3, this is called step 4. 4 steps. This is called step 1, which we explained in the class. Step 1. This is called step 2 knowledge. This is called step 3, EYS knowledge. This is called step 4. Nicely we got a graph like this. So I think this graph is telling it is not a good behavior which is working like an ideal inverter. Ideal inverter if you want, this value has to fall at the center. And not only it has to fall in the center like non-linearly, it has to fall like a linear graph. But in current saturation, it is falling like a non-linear. Whenever you will fall like a non-linear, you are taking more time to be in active region. But for a good inverter switch, on to off when you are going, you should not spend the time in active region. When you are going like a parabola, means you are spending the time in active region, where it will reduce the speed of your timing, called switching time. That's why it should be like a vertically just fall, linearly. But that is not happening in this case. That's why in digital design part, whenever the persons want to design a good inverter, we never take a passive load cycle. We are going for a new technique today called as active load technique. What is the meaning of active load? I'll explain you. Passive loads are not good because the transition is non-linear here. In current saturation, first drawback you can see, drawbacks I'm writing here. First drawback, in current saturation, V0 decreases non-linearly. This is one drawback. We should not fall non-linearly, we have to fall vertically. That is called linearly we have to fall. Because in ideal inverter I have shown you, vertically I am falling from on to off to on without spending the time in active region. This is one drawback. And the transition, the on to off, or off to on should happen at VDD by 2. When the input is at VDD by 2. This is also not happening. When you want to become on to off or off to on, exactly the switch should be at the center, the transition has to take place. It has to move on to off and off to on. But here, After VT, the MOSFET is coming immediately into on, which is in current saturation. After that, is going to the triode. So that is not a good idea. These two things are not happening in the class. These are the two drawbacks we are getting. So how to improve this idea is important today. So the first idea is a failure idea. NMOS is an inverter, but it's not a good inverter according to our ideal inverter behavior. Okay? Who is understanding this point? Nicely, will understand the second step called as NMOS inverter with active loads. That means we are removing this idea called passive loads. Now we are keeping a transistors in place of a resistors load. What happens? Then we'll see the next idea. In place of keeping resistors, today we'll keep the transistors now. Is there any better improvement will come in the graph? Let us observe it. It is easy now to understand because main concept is ready. So take the graph properly, concept. This is about my first inverter design called NMOS inverter with passive load. Anupam Das, you should not ask like that here. Mind saying that? You got that one. That is wrong statement. 0 to suppose 2 volts is off. But that is not happening in general inverters. That is a MOSFET as a load. But this load is not working like inverter. It is falling like linear like this. So there is a better improvement in the concept. In place of non-linear falling, linear line will have more slope, non-linear line will have less slope. Ideally, we want just only the story of middle one will see. If M1 can here, we can cancel it. Both K's are same, we can cancel it. Yes, sir, Pito, what you said is correct. In this concept, M2 is fixed. In all the regions, it is in current saturation because it is fixed by biasing. I have fixed it voltage, but M1 will change because it works like an inverter. That logic is simple. So VGS1 is what here in the board. Carefully see what is VGS1 and what is VGS2 by deco. Here, this is your gate, this is your source. We'll take this as VGS1. This is VGS1. And this is VGS2. This is VGS2. What is VGS2 here is, this point can I take here, VDD. This is VDD because this is VDD. This VDD is here, VDD minus V0 is VGS2. So VGS1 we can write as VIN in the problem. VGS2 we can write as VDD minus V out. So that point we are writing here. So that point we are writing. VGS1 we'll write as VIN minus VT whole square is equal to VGS2 we can write it as VDD minus V0. We are taking this value difference. VDD minus V out minus VT whole square. So this is the way how I have taken the concept. Okay. If you take the square root here, if you take square root both sides, we'll get VIN minus VT becomes VDD minus V0 minus VT. So the space will be gone. We'll have a straight line equation like this. It's a linear equation. If the threshold is same on both sides, if the threshold is same, then your output you can write it as VDD minus VIN will be the equation. So can you see that this is a relation we are getting in current saturation to current saturation. So if two transistors are in current saturation, your input, suppose if you are increasing, the output is decreasing, but it is linearly, it is happening. So this is the proof, background proof for you. Why it is falling linearly? This is the small mathematics for it. Okay, it's not falling like a parabola, now it's falling like a linear line. VDD minus VIN is equal to V out means as the input increases, your output will linearly decreases. So this is the concept behind your second topic. So I completed very smoothly this topic without any extra calculations. Just only I taught you that middle technique, why it is changing linearly. Other things are same, what you have studied till now. So make it minimize like this, switching techniques. So with this I covered the second concept. So we have only one drawback in this topic. Linear falling we are achieving here. Okay, it's falling linearly, that is good. But one thing, that linearity should fall from the center is important, but it's not falling from the center. So the only drawback in this topic is it is not falling from the center. And not only that, it has one more disadvantage. Are you thinking that this answer is VDD? Most of the people will think that this is VDD, but this is telling that it is not VDD, it is minus VT is coming. So this point is very important to learn. So we are not getting the highest voltage in this switching technique because of active loads. Here we are not getting the highest VDD, minus VT is coming because this MOSFET is already on. This load is, this M2 is already on with the threshold voltage VT. So already it is having some threshold voltage. That's why highest voltage minus threshold voltage is your output. The second transistor is not off here, we have biased it already. It will have some minimum threshold voltage inside the device. So we have to subtract the threshold to tell the highest output. So this is one of the drawback of this concept. The previous topic we are getting highest voltage but we are not getting now. Suppose VDD is at 10 volts, threshold is 1, we will get 9 volts in this concept because of active load. Roy, how you will ask these questions here, Roy? इधर बोर्ड में clearly नहीं देख रहे क्या? These transistors are in series. When two transistors are in series, compulsory ID1, ID2 current will be same or not? वो doubt क्यों आ रहा है यार आपको? Clearly देखते समझ में आना. They are not in parallel, they are in series. That's why I have taken ID1 and ID2 same, and I have been calculated when they are in saturation. This is the way of answer I am expecting. Okay, right? One time when you are asking a question, just एक बार observe करो concept को. बोर्ड में इतनी clear है. ID1, ID2 are equal by because they are in series. Here M1, M2 are in series. Then how you can ask that question? M1 and M2 are in series. When they are in series, we can write ID1 equal to ID. Roy, I think you understood it. Okay? Don't expect this type of questions here. Clearly, it is showing series there. So complete this. We are coming to the final stage now. This is also not giving a correct view. Just we'll write the drawbacks and we'll start designing the last topic. That's called CMOS inverter technique. That will help you to do the problems on these circuits. Hardly 3 models, 2 models I completed. The last concept we'll apply. Oh yeah, मैंने बता दो 70 I'm writing the drawbacks. Wait. The first drawback is this linear line has to fall at the center VDD by 2, but it's not falling. Okay. Second point is it has to get the highest value VDD, but it's not coming. VDD minus VT is coming because the active load is having a threshold voltage when it is an on condition. So we have to subtract the threshold voltage to get the output voltage V naught. So these are the two basic drawbacks. What is that slightly different like beta? अनुपम दास इधर beta किधर से आया आपको? बोर्ड में beta किधर बोलिए? अब बोर्ड beta बोल रहे हैं. Where is beta here? Beta is a word comes in BJT classes, not in MOSFETs. Beta is a current gain in common emitter transistors. इधर betas नहीं होते हैं because it's at MOSFETs. Yeah, अनुपम दास maybe sometimes exams में threshold voltage same भी दे सकते हैं, threshold voltage different भी हो सकते हैं. Okay, ideally we can say threshold voltage will be same, but practically not possible. Slightly different हो सकते हैं. Okay, here I assume that they are equal and I solve it. So let us write some drawbacks. I think here only I write drawbacks. You can note down drawbacks. I write here 2 points, basic points I'm writing. First point, the switch off to on or on to off is not happening at VDD by 2. This is one observation. The switch off to on and on to off is not happening at VDD by 2. It's just getting on at VD only. At threshold voltage only the switch is getting on. Threshold voltage generally different होते हैं, slightly mismatch होते हैं, but theoretically we said both are same and we'll study the classes. Okay? We'll say different, slightly different like okay, you want to tell that beta story in BJTs? Yes. The betas, whatever you say, slightly your threshold voltage can change, KNs will change, slightly mismatch. They're all called mismatching parameters. Slightly different हो सकते हैं. The second point, this is one point here, is not happening. Second point, point number 2. At Vi is equal to 0, your output is coming as VDD minus VT. This is a drawback. Actually, we are expecting output should come as VDD, but in these problems we are getting VDD minus threshold voltage because the second MOSFET is on. That's why we will have some threshold voltage drop in the MOSFET. You have to subtract that to get the output answer. So if I want a 10 volts highest value, you might not get 10, you will get 9 volts because threshold voltage is 1 and we have to subtract it. So these are the two basic drawbacks again coming in this model. These are the two basic drawbacks we are seeing. The last topic, I'll teach some half an hour class. By 4:30, we are going to close the matter of MOSFETs. After that, you can take a small break. We'll start doing the problems based on the MOSFET and we'll close the matter today. I'm expecting tomorrow freshly I'll start the amplifiers. Today it is not required to start. Tomorrow morning only I'll start the new topic because I have to record this video as a new video for the new chapter. That is the main reason I cannot start the class today. Tomorrow we'll start the class. Maybe today also, I'm expecting the class really by 6 o'clock we can complete. Today also. Okay? By 6 o'clock we can close the total concepts. So let us start the final journey on this MOSFET. The final journey I'm doing. Let's start the final topic. You can give the heading C. Concept number C. One of the best important topic in electronics, which is called CMOS inverter recall. We call this as CMOS inverters. One of the best inverter in electronics because this will behave like a ideal inverter. Ideal inverter. This only is behaving like ideal. That's why most of the digital electronic circuits will behave or will design with these inverters. Today class I'll demonstrate how it became an ideal one. This is the last topic. Whatever the graph I teach today, that is more important to solve the questions today. Okay? The transfer characteristics will keep in mind from where to where which MOSFET is moving and which MOSFET is at what place in which region. Then these problems are easier. So try to understand the trick. His amplifier is linked with MOSFET. Yes, Satyam, MOSFETs are not only switches, they work as amplifiers also, friends. Okay? But BJTs we use like amplifiers most, switching we use less. But this will work as a good switch. At the same time, it can work like an amplifier also. MOSFETs. Yes, yes, Akshat Kumar is like a logic families. Yes, similar to logic family techniques, but I'm not teaching logic families. I'm telling you that how it is created, the switching characteristics. What are the tricks they applied to get an ideal characteristics? With the help of the knowledge of analog concept, we are teaching these ideas. Okay? So let us see. Let us see the final topic. So how to design a CMOS means it's very simple. First above, I take one MOSFET. I take one MOSFET here. That MOSFET should be a PMOS. So source has to go up here. This is source. Always source should be top, drain should be bottom. This is VDD I'm taking. This is source. This is a drain. This is one way of showing the PMOS symbol. First I have taken PMOS in the top. In the bottom, I take NMOS here. I'm taking here NMOS. Here again drain is there. We have source. And just I'm making a closed package like this. One NMOS and one PMOS, just I pack it. And I'll give at a time the input for both at a time. This is the story. And I'll take at a time the output at the drain. See the trick here? M1, this is M2. This is M1, we take it as a NMOS now in the class. And this we take it as a PMOS. Carefully understand the trick here. This is gate. This is gate. This is also gate. If you correctly see, it's a package of two MOSFETs. It's just a package of two MOSFETs. One is an NMOS, one is a PMOS. PMOS should be kept at the top, NMOS should be kept at the bottom. And both has to give the same input. Both has to couple it first at the gate to get your couple, and the same input you go at the drain you take the same output. That is a beautiful design called as CMOS inverter switch. How it is going to give a good result for us, let us understand it. Why it is giving a good result? If I do like this, what is the benefit? We'll try to see. Okay, write carefully up to here. First I'll show you the graph, then I'll explain you how it is falling by VD, D by 2, that I'll show you. First of all, seeing the board, some observations I'm doing here. This is VGS, you can see here. This is VGS. This is VGS, from here to here. This is VGS. And here also, we have VGS, from here to here. This is one VGS we have, here one VGS we have. Okay, and we have here VDS, you can see. This is VDS. But have you seen that this VGS are different. This VGS, we'll keep it as number, VGS1. This we'll keep it as VGS2. And we'll write this as VDS1, and we'll keep this name as VDS2. Correctly, if you see, all these drops are different from the board. Carefully understand the drops first. If you see the drops correctly, VGS1 is nothing but input minus 0 is VGS1 we are seeing. But VGS2 is nothing but VDD minus, sorry, you have to take from here. VIN minus VDD is VGS2. That's why the VGS drops for PMOS and NMOS are not same, seeing the board. So we'll write the points first. VGS1, seeing the circuit, we can write it as VIN minus 0. So it is VIN is the first point. Point number 1, seeing the board you can write. First point. And the second point is VGS2 is how much? VGS2 is nothing but it is a VIN minus VDD. This is your second equation. VIN minus VDD is VGS2 in the class. Okay. Next, what is VDS1? VDS1. VDS1 is nothing but your V out is VDS1. Correct. The last point we have VDS2. Last point is VDS2. If I want to find VDS2 here, we can write it as VDD. VDS2 means, be careful, you have to start from here now. This is drain to source. So I think you should write it as, not VDD, we have to write it as V out minus VDD you can write. So these are the 4 basic steps. Seeing the code we can understand it. So that means the VDS1, VDS2 are not same in the CMOS design, and VGS1 and VGS2 are not same at any instant of values. All are different. So have this knowledge. I think now it will have one EOS boundary. It will have one EOS boundary. So next point is NMOS will find out the boundary. NMOS EOS boundary is how much? We'll find out first. NMOS clear will have one boundary line, and PMOS will have one EOS boundary. That is moving from triode to saturation, moving from saturation to triode, because both are working as inverters now. This is also working as an inverter. This is also working as an inverter because both sides we have given the input. Previously what we done is one we have fixed it, one we are operating, but now both we are operating at a time. So both are working like inverters. That's why NMOS inverter, if you use, what is the EOS boundary for it is? Already we studied. VDS will become VGS minus VD. This is the boundary. VDS value here is V out. VGS value is VIN minus VD. This is one boundary for NMOS. We got a straight line equation in the graph. This is one equation you can take. And the PMOS boundary if you want. PMOS. If you consider for PMOS EOS boundary, we can write it as, what is PMOS boundary? It is also same. VDS is equal to VGS minus VD. For both the cases, the relations will be same. But signs will be different, we'll see that. VDS is how much here? This is VDS1 you write. This is VGS1. Here we can write VDS2. This is VGS2 minus VD. This is the second boundary technique. Okay? What is VDS2 here? This one. VDS2 is nothing but V out minus VDD is equal to what is VGS2 here is VIN minus VDD will be the relation. You can see the boundary relation again. We are getting. So you can write here V out minus VDD minus VDD. This minus VDD will be cancelled, and the output will become VIN minus VD. We are getting. Correctly, if you see this relation and that relation, we are getting same answer. But there is one difference in the class is here the threshold voltage will be positive for NMOS. But here, my threshold voltage will be negative for PMOS. These are the things we have learned in the classes. The threshold value for enhancement modes, if you see, this will be positive, that will be negative. Therefore, your V out, if you apply the sign there, it will become VIN minus of minus VT. So your output will become VIN plus VT. So this is the story of your boundary lines. So one is NMOS boundary line, one is PMOS boundary line. You are getting two different lines. So this is the small mathematics before starting the graphical analysis. So please complete up here. Very small observations there. Up to here I think it's clear. Just only boundary lines I created. That means in the graph you will have two boundary lines. One line will come from VIN minus VT, one line will come from VIN plus VT. One is a boundary line for PMOS, one is a boundary line for NMOS. Let us see the graph now, how I draw it. With this idea, the graph easily you can draw it now. So if it is completed, please tell me. Let us finish the graph with each and every region. How will I identify? Try to understand it. शब्निदास थोड़ा लॉजिक यूज करो. आप बोल रहे हैं VDS2 is a VDD minus V out आप बोल रहे हैं. मैं क्या बोल रहा हूँ? V out minus VDD because I'm talking here D to S not S to D. थोड़ा वो terms देखो यार. It is not VSD I'm talking here VDS because everywhere I teach VDS on. When you are talking VDS, this is higher potential, this is lower potential, my friend. Okay? It is not VDD minus V out. If you want to write the answer, the value should be VSD2, not VDS2. Okay, Sravnidas, I think a slight confusion you made by yourself. So terminology is very important. Okay, got it? Great. So let us see the graph now. Let us see the very important graph, the total CMOS graph. You can draw a total page you can cover. You can take a full page and draw this graph, which is very important to solve the problems in the GATE exams. This one graph will solve each and everything in the problems. So write neatly this graph. This is VIN. Take the full page. Make it horizontal page otherwise. And write nicely this graph. This is V out. Take the entire graph like this. Okay? Each question I can solve with graph only. Knowledge is that. So let's see how the graphs are coming. First one, 0 to threshold. This is one threshold we have. From this, we have a line for NMOS. This is an NMOS line. This is your NMOS line, which is V naught equal to VIN minus VD, which is for the boundary of NMOS. चलो ये concept मालूम है हमको. This is for NMOS line. Whatever PMOS means, he said that it is a VIN plus VD. So 0, you are getting marking here, now plus VD. See here, minus VD means you start from x-axis. VN plus VD means you are starting from y-axis. Because when I keep input 0, the output become VD in PMOS technique. So the line will come like this. There is another line. Parallel to this. This one boundary line will come. This is output is equal to VIN plus VD. This is for PMOS. So one boundary is for NMOS, one boundary is for PMOS. We'll take different colors otherwise. We'll make it a colorful this graph because it's a very beautiful graph. This is for PMOS. We'll take another color. This graph is for NMOS boundary. This is for NMOS boundary. These are the two boundary lines I have been predicted in the class. Okay? Two boundary lines. Now the student should be able to understand the logic. What is the logic I told is, your M1 is NMOS, is doing the same work. Till now what it has done, it is doing the same work. What is that? It is getting a switch off M1, so it is getting the highest voltage VDD. The problem has been solved, called minus VT problem is solved, because here no switch is in current saturation. We are not fixing current saturation, both the switches are moving. So we cannot have threshold voltage here. So we have VDD directly. That is an advantage we got. If one is fixed with current saturation, you have to supply threshold voltage. But no switch is in current saturation initially. So we have VDD, highest value is coming. After this, up to this, we can write your M1, which is called NMOS, it is in cutoff. Whatever we studied, same story. M1 is in cutoff. But M2, whatever you are seeing, is in which region? Somebody asked me, then how will you verify it? How to verify the concept now? M1 is in cutoff, that I understood it. But M2 is in which region? If anybody asks this simple question, what is the trick for this? You can go back and see your diagram. Your output became, you said VDD here. Your output became VDD. This is also VDD, this is also VDD. Then what about VDS to answer? You got the highest voltage VDD. And he's asking this difference. VDS is how much for PMOS? Have you seen that? This is also VDD, this is also VDD. That means your VDS for PMOS, we are getting 0 volts. Whenever VDS comes 0 volts, we call it as ohmic region. That means you are starting from ohmic. That means when M1 is in cutoff, my PMOS switch will work in ohmic region. That is the story. I hope you understand my concept. When this is VDD, this is also VDD, the difference is 0. When you said 0, when VDS is 0 or millivolts, the MOSFET will work in ohmic region in electronics, I said. So the trick is easy. The trick is very easy to understand it. So let us move the technique now. So M2 will be in ohmic region, it started. So one is in cutoff, one is in ohmic. The game started like this. When NMOS is in cutoff, M2 is in ohmic region we got. You know the trick then? M1 will go to cutoff, next will be current saturation, next will be triode. But M2, it started from ohmic. Then it has to go to triode, it has to go to current saturation. That is the story. Means it has to go reverse to the NMOS. That is the trick. So whenever you are coming up to this point, can you see that your M1 will reach to VT if you cross, M1 will come to current saturation naturally. M1 is a NMOS switch, will come to current saturation. That is the knowledge we have. But M2 cannot go to current saturation immediately because after ohmic, it will have triode. So you will have a non-linear falling like this. From here, you are going to see a non-linear fall. From this point, you are going to see a non-linear fall like this. This is the non-linear fall. Why it is non-linear here is, these two regions are not matching, that's why it is non-linear. Here we are getting M1 came to current saturation, it entered into current saturation. but M2 just came to triode first. Because if you don't touch triode, how can you go to current saturation? So in that area, M1 came to current saturation, M2 came to triode. My triode equation is different, current saturation equation is different. If you equate ID1 equal to ID2, we are not getting linear equation. That's why it is non-linear falling we are getting. समरेश थोड़ा आप लॉजिकली मैथमेटिक्स थिंक करो, आपको लाइन आ जाएगा. When input is zero, your output is threshold voltage. Just straight lines I'm drawing here. तो straight lines ड्रा करना कैसे एक बार प्रैक्टिस करो, सब्जेक्ट आ जाएगा. Basic things है ना straight lines. When input is zero, output is threshold. So from that I have written a line. And the second case क्या है? Input is zero, output is minus VT. From here I intersected the line like this. So it's a part of intersection lines. Okay? उनमें confusion नहीं होना यार. So this portion is not linear because both are not in current saturation. If both are in current saturation, you get linear. But one is in triode, one is in current saturation. But when you touch this point, can you see that from here to here triode region is completed? But this is a boundary to tell triode to current saturation will vary. Therefore, M2 will move to the current saturation here. Already M1 is in current saturation. So from this point, you see a line like this. From this point, it will sharply fall like this. This is the way of falling. Linearly it is falling from this point to this point, saying that in this portion, M1 and M2 will meet in current saturation. This is the story actually. Exactly, they can meet in current saturation. Because when M2 crosses this, it will come to current saturation. But M1 to come to triode, this line has to cross. So below this line, M1 will be in current saturation only. But M2 has crossed already the current saturation with this boundary line. So we got a linear because of M1 and M2 are in same region. Again from this point, we have another graph. From this line, you can see it will fall again non-linearly like this. So here we can say M1 will come to triode now. The boundary line you cross, so M1 will go to triode, but M2 will come to current saturation. So how to remember this trick? Correctly see the trick. Remembrance trick you can see. So I have to take one good color for this. See the trick. First, इधर से देखो current saturation M1. Here also current saturation, but which is changing here? Your M2 is changing with this boundary line. So M2 is changing with this boundary line. Okay, triode to current saturation it has played the game. But whenever you come from this line to this line, can you see that here which is changing is M1 is changing from current saturation to triode. Like this, you have two transitions are going on. When you touch this line, one transistor will change the transition. When you touch this line, it will change the other transition. This is your CMOS graph technique. Okay. Now we have to prove in the class how much it is falling exactly. These people are telling we can make it fall exactly at VDD by 2. We can fall. They are telling. Let us prove it exactly whether I can fall here or not, and what are the conditions for that. So I will do some mathematics for that. I don't want to teach extra things. Only the middle one, why it is falling linearly, and at what time it is falling. Just we'll see the status. If M1 and M2 are in current saturation, only we got the linear line. In other regions we are not getting. Both should be in current saturation. Then only we get linearity. The first equation is ID1 should be equal to ID2. You have Kn1 into VGS1 minus VT whole square is equal to Kn2 VGS2 minus VT whole square. Actually, this is your equation. When M1 and M2 are in current saturation, I have to prove that exactly my input should be at VDD by 2. Then what I can do is, if I suppose design in such a manner, so this is not a Kn1, Kn2, sorry for this. This is not Kn1, Kn2. This is Kn, this is Kp actually. So now what is your job in the class is, your Kn should be equal to Kp you have to design. That's the first condition. Okay? Kn should be equal to Kp you have to design. So Pandit here, VDD, why we got the answer is, here highest value, we got VDD, we are not getting VDD minus VT because the transistor is not in current saturation, second transistor is not in current saturation, it is just an ohmic effect. Ohmic means you have VDD values 0 volts. Okay? Sorry, VDS values 0 volts. When it is in 0 volts, I think the output will be VDD only, highest value. Because ohmic means what? The difference is 0 there. But when you are in current saturation, I told that there is some threshold voltage. That's why the difference. Here the difference is not coming. That is a drawback have been rectified with this technique. Okay? Ohmic means threshold is not required to subtract. If it is a current saturation, you have to subtract the threshold voltage. Okay? Here the main job you have to do is K and Kp you have to make equal. If both the transistor K and Kp if you balance it with the W ratios and the mobility of electrons and volts, then automatically you will get this equation as you will get like this. If K and Kp are same, you will get the equation like this. Okay? So if this is you can take T and Tp you can take, then what I will do is not only this, Vtn we will make it as Vtp. The threshold voltage of N MOS I will make it equal to threshold voltage of P. Then that also same. If squares if you cancel, you will get VGS1 minus VT is equal to VGS2 minus VT you will get. VT, if I take equal, that will be cancelled. So what is VGS1 in the board previously? We just write down. What is VGS1 here? VIN. What is VGS2? It is VIN minus VT. Okay? This is VIN. It is VIN minus VT. VDD. Okay? You can see the proof now. It becomes, I think somewhere written mistake. VGS1 is VIN. VGS2 is VN minus VDD. Correct? Where I've done small mistake, I think. VGS2 value is how much? VGS2. VGS2 is VN minus VDD. So please copy up here. A small mistake happened, I think, somewhere. Please identify it. Is there any mistake I've done? Sir, ohmic M2, how VDD comes. 7 is I'll tell you that again separately. Yeah, I think, VTP will be minus VT, correct? Correct here, VTP should be minus VT. So I think by mistake written this one. Let us correct it. Let us correct this point. Okay. I'll write this answer as VGS1 minus VT will be equal to VGS2 plus VT will take. Minus of minus, it will become plus. Majumdar, again I'll explain, don't worry, first get me this proof. Why this is not getting the value, I'm just observing where the mistake I'm doing, just I'm observing it. You said that minus, we made it as plus, that is okay. Then anything I can change here. VT we got. VGS1 minus VT, here VGS2 minus became plus. What I can do now? So VGS1, we can write it as VIN minus VT is equal to VGS2 is VIN minus VGS2 plus VT we got, correct? VGS2 plus VT. Okay. This will become VIN plus, what is this? VIN plus VDD. VIN minus VDD, so this is minus. VIN minus VDD plus VT. Correct? So, actually here problem carry means VN is getting cancelled. That should not get cancelled. According to this mathematics, that should not get cancelled. Where I'm doing mistake, just have to think about this now. Total concept is correct. Somewhere mathematics is going mistake. Let us try to investigate that one. Somewhere we can investigate that. You also try it and get me this answer. Input should be equal to VDD by 2 has to come. Just try it one time. Where the mistake I'm doing. No iron, VD should not be VDD by 2. Somewhere mistake is going on. किधर mistake हो रही है बात करो. Otherwise, we'll take some break. In the break time, just I'll roughly do it and see where the mistake is going on. That mistake we'll correct in the short notes techniques. Okay. The next I think we have to do what to practice. So small short notes. I'll explain again all these things related to that. In the break time, just I'll verify this condition where the mistake is going on. Okay. Meanwhile, you also try कर दीजिए. Yeah, I think yes. Sorry, correct. Yeah, correct. Somewhere mistake is sign technique mistake we have done. Exactly correct. Sign mistake we have done. Repeat. So what is the mistake I think I've done in the class? We'll see that here VGS1 should be positive for NMOS I think, correct? VGS1 should be positive for NMOS and VGS2 should be negative in case of PMOS. This for NMOS and PMOS sign techniques are different. Maybe that mistake I've done. This is for NMOS, this is for PMOS. That means VGS2 we have to consider it as a negative value. Okay, maybe that is a sign difference we are getting. Shavik here K and KB are different, but we can adjust it by the W by L ratios and mobility of electrons and holes. If you balance the two ratios, definitely we can make it equal also. K and KB we can make it equal. So let us apply it now. Whether it is correct or not now. What we'll do is K and KB both are equal. We'll take here K is equal to KB will balance it. And VGS1, what is the value we got? VIN minus VT will take. Make it VTP and VT and both are same you take. So VN minus VT you take. And coming to this equation, it will become minus VGS2. Here minus VT is there inside. Let us, if I make it square times here, this is also square. Can we have a common term here? Vn minus Vt is equal to, minus if you take common, it will become VGS2 minus Vt whole square. Just minus if you take common outside. If you take minus here, common, if there is no square, again it will become VGS2 minus Vt whole square. Correct? VGS2 plus Vt whole square you get. VGS2 plus Vt. Minus of minus it will become plus. So, Vn minus Vt. So I think this answer you have to write it as, VDD minus reverse if you write VDD minus VIN minus VT will come. So VT you can cancel it. So 2 VIN is equal to VDD. So VIN should be equal to VDD by 2. So finally some sign confusion happened. You just correct it and see that the answer finally will be expected to be VDD by 2. Maybe one more time I do this mathematics for you. After the break where the mistake happened. So finally this answer has to come. Okay. Just only thing is minus VGS to make it reverse this value. VDD minus VIN you write. That minus VT will get cancelled. Then we get the story VDD by 2 will be the